The Robert Scott Bell Show.
You know, I get to talk to a lot of smart folks on this show. I mean, some of the greatest minds on planet Earth. Sometimes they're within the scientific academia, and they actually have PhDs by their name. Now, they're not always smart, but the guys and gals I feature that have that, you can bet they know what they're talking about. And they also have a way to communicate what's so vitally important here, validating the things I've been talking about for many years. Now, one of these people is David Rasnick, Ph.D. He is also connected with Professor Peter Duesberg and others that we've interviewed on the subject of AIDS, the fraud about HIV, etc. And he is also, I don't know, David, did you actually work with Peter on his book, Aneuploidy, about aneuploidy? It's like oncogenes, aneuploidy, and AIDS.
Actually, that was Harvey Bialy. You know, he actually...
That was Harvey. Okay,
yeah,
got
Harvey Bialy wrote that book, yeah.
Thank you. I knew that all the names were running back through, and it's been a while since I interviewed him on that subject. But this concept of aneuploidy, because we're going to get into what cancer is, and David's working on a new book, and he's asking for your help for completion, and you could be part of this, and I'm encouraging it, I'm endorsing it, and absolutely I want you to take part in this. But David Rasnick has also been part of the developing team. You might have to give a little backstory on how you came up with these protease inhibitors that you would probably never really use, but in your early years when you were part of that establishment, and this drug category became big in the era of AIDS.
Right. In fact, before 1984, the field of proteases, I was a big frog in a small pond in those days. I knew virtually everybody in the world who worked on proteases. Proteases are enzymes that, like a pair of scissors, that cut protein, either digest them, like in your digestive tract, process them, blood coagulation, hormone processing. Anything that has to do with processing proteins, proteases are involved in. I was particularly interested in the tissue-destroying diseases like arthritis, emphysema, parasitic diseases, and cancer, where you get tissue destruction, and the proteases are the principal culprits involved in the tissue destruction. And as a chemist, I designed inhibitors, some pretty good ones, in fact, for these proteases for those various diseases. And but it was not a political area in there prior to 1984 in the AIDS business. It was a reasonably small area. It wasn't politically charged, and you could say whatever you wanted to, and you have very nice heated debates and things at conferences. But you'd be buddies. You know, you didn't hate people. You allowed everybody to say what they wanted to. You go out and have a beer with them afterwards.
Right.
AIDS changed everything. You know, now everything is sort of dogmatic, and if you go in a conference, you have to. Many things you can't say and you can't talk about. You can't bring this up.
It's become more like a religion or a cult. It's not science any longer, right? And yet you still have that scientific. I would say scientific gene. I'm not a genetic guy. I'm an epigenetic guy, right? and yet, you know. And I love science, and I love people who genuinely invest in science for the sake of we want to find out what are the facts here and what do they reveal, what do they lead to. And when Harvey came out with that book on aneuploidy, and then I interviewed him, and then of course Duesberg on it, he talked about chromosomal abnormality. Something was going on; it was manifesting things in a corrupt manner. Now, there's also the other aspect of that oncogenes, right? The idea that there were genes responsible for causing cancer or even curing cancer. And I said, this doesn't make sense because we see environmental factors altering genetic expression all of the time. And now we get to this concept of aneuploidy, and you're calling in your new book that you're working on what cancer really is, a chromosomal imbalance of some kind. Can you describe for the lay audience what that is?
Yeah. Each species has its own specific set of chromosomes. Chromosomes are like volumes, like the Oxford English Dictionary. I think there's 23 volumes in the Oxford English Dictionary, and there's 23 volumes in human chromosomes. And each one of these chromosomes has an average of about 1,000 genes. The smallest one is like a couple of hundred genes. The largest one, chromosome 1, has about 2,000 genes. But they're divided up into volumes called chromosomes, and it's those chromosomes that are all messed up in cancer. Normal human cells have 2 pairs of 23 chromosomes. 23 comes from the mother, 23 comes from the father, and every cell has the same makeup of these 23 or 46 total chromosomes. Cancer typically has 60 to 90 chromosomes in the nucleus. I've seen as many as 1,000. Now, each one of these chromosomes, as I said, on average one has about 1,000 genes, and nobody has ever demonstrated that a handful of genes, 1 or 5 or 6 or 7, however many there are, normal or mutated, can turn normal cells into cancer. Yet that is the current theory that drives virtually all of cancer research in the United States, is the idea that cancer is caused by gene mutation, even though it's never been demonstrated that they actually do that. Peter, he and I have revived an old theory of cancer called the chromosomal theory of cancer. Cancer basically is a disease of the chromosomes. It's an abnormal number of chromosomes that are out of balance. There's nothing new here. David Hanselman observed these abnormal chromosomes back in the 1890s. He had very nice drawings of this. And Theodore Boveri even wrote a monograph in 1914, the year World War I started, where he laid out the chromosomal imbalance theory of cancer. He didn't call it that, but that's what it was. And virtually everything that he said, he got right.
Yes.
The problem was that World War I started that year, and he died the very next year. So it sort of had no way to really go forward.
Almost lost to history at that point.
Almost lost to history, and a fellow by the name of Wingy brought it back. I forget when, a little bit, but he was totally ignored. And then George Papanicolaou of Pap smear fame, also, he didn't develop the theory, but he used it. A lot of people don't know this, but Papanicolaou, his Pap smear, he uses this as primary method of diagnosing cancer. It's the size of the nucleus. That's the principle. There's other things that he combines with that. But all those extra chromosomes in the cancer cells typically make those things 2 or 3 or 4 times bigger, the nucleus of these cells, than normal cells. I even have a couple of pictures on my website where I show the normal cervical cells, and I show cervical cancer cells. They're several times larger, the nuclei are, than the normal cells. That's the Papanicolaou, or the Pap smear.
Right.
That's how they diagnose cancer. And they're crammed full of chromosomes. That's why they're so big. And George Papanicolaou proposed that it was those extra screwed up chromosomes that caused cancer. But he didn't push that. He basically used that fact to diagnose cancer, and it's still one of the best methods of diagnosing cancer today.
David, by the way, we're talking with David Rasnick, a good friend of the show here. We haven't had him on in a while, but I'm going to have him on a lot more with this new book coming out, and I want you to participate in helping him finish it, if you don't mind. Go to davidrasnick.com. It's in the show notes at robertscottbell.com. The book he's working on, Precarious Balance, What Cancer Really Is, and we're getting a sneak preview into it. Now, what are the concepts from chromosomes? I heard the term exosomes as well. Is that related to this in any way, shape, or form?
Well, not tremendously. The thing with the chromosomes is that it's a massive alteration. You don't have to worry about little bits and pieces here and there making all the difference. When you have like 50 extra chromosomes in the cell versus what was normal, you shouldn't be surprised that the cell is really out of whack.
So it's significant. It's significant. Now, David, the next question is, if we're looking for a cause of cancer and we blow out the gene cause of cancer theory, and we say, all right, well, what would cause these chromosomal aberrations, abnormalities, or imbalances? And now I think we'd be onto something.
Yeah. Well, it's very simple. All carcinogens that have been tested cause abnormal numbers of chromosomes. It's that simple. And one of the disturbing things is virtually all I think, in fact, every chemotherapy drug that I've ever looked at is carcinogenic. They use these drugs to disrupt normal cell division. Because you can't, they try to disturb the cell division of cancer cells, which is easy to do, but in the process, none of these drugs know whether it's a normal cell or a cancer cell.
Indiscriminate kill, yes.
Indiscriminate kill, and they disrupt these dividing cells, and as a consequence of doing that, they generate even more aneuploidy or more chromosomal imbalance, and even generate more aneuploid cells or cancer cells from normal cells. In fact, 1 in 6 new cancers is caused by cancer chemotherapy.
Yeah, which is why we said here, oncologists are not the cure for cancer, they're the cause of it, another contributing cause of cancer. And
they are.
The other thing I'm just thinking of, because I got a sneak preview of your first chapter in progress, and you said something I had never read before, that there are no two cancer cells that are alike. They're like snowflakes. Every one of them is different, and it never occurred to me. And if that's the case, why is that the case?
Well, the thing is that once you get, I try to come up with these various analogies to help people understand what's going on. If you have a wheel that's totally balanced, let's say, and you roll it down the road as it goes round and round and round, nothing happens. Now, if you get a dent in it and you keep rolling it down the road, does it return to its normal shape? No, it gets more and more dented. And it's like you can't unscramble an egg, that sort of thing. Once you get an imbalance in chromosomes, if the cell can divide, these cells that have abnormal numbers and unbalanced chromosomes, they're not very healthy cells. They're damaged cells. Thank goodness most of them don't go anywhere. They stop dividing and they die. Right. Occasionally, though, they will get a combination of these abnormal chromosomes that will persist to some degree. And when these things divide, you get two new cells that never existed before with a combination of chromosomes that are unique. If those two, one or both of those two now divide, you get now 4 cells that never existed before. It's like cutting a deck of cards. It's out of whack and you start cutting it. You can never cut it and get it back to the normal 23 pairs of chromosomes. Mm-hmm. And then that progresses over many, many cell divisions to generate, 1 trillion cells or whatever, and no two of them are alike.
Right. Well, in the containment of the immune system is... Well, it's lost at that point. And what we've got to do strategically, when we understand what you're talking about, aneuploidy or chromosomal imbalance, it's going to change the face of, I believe, cancer research in terms of acknowledging that we can't look to poison the body back to health. We've got to look to say what caused this chromosomal abnormality. We look at those things that are considered carcinogenic, toxins, poisons, pollutants, and also what are the role of nutrient deficiencies, mineral deficiencies in aneuploidy. And, David, I've only just warmed up with you, and we're almost out of time here. I'm going to talk with you more on the break. Everybody, there's an Indiegogo campaign. Please participate, whatever little you can. Help David finish this book. This will be a groundbreaking new book on cancer. It's called What Cancer Really Is. David Rasnick, my friend, so great to have you back.